Hello and welcome to the video. We'll be covering the random vector independence transformation invariance theorem. So let us have some collection of random mutually independent variables indexed by some index family I, and let us have an equal amount of transformations of the real number line GIs. Now, and let these transformations be measurable. Then the collection of the transformed random variables is also mutually independent. The vectors therefore are. Now, the proof is simple, and we shall prove it by definition. So we have that let J be some subset of I such that J is finite. Now, by definition, you want to prove that the probability of the intersection indexed through J, or indexed over J, of the sets of all those omega in omega, which is our probability space, of which the random variables xi's are defined, such that Gi composed with xi of omega is contained in some set bi, which is some subset of the real number line. It's some interval, right? This is equal to the probability of the intersection, the same indexing, of the set with the same underlying set, but we write xi of omega is contained in the preimage of bi under gi for all i's, right? Now, it is easy to see that these two sets are in fact equal. A picture will make this clearer. So we have our omega and some subset of the real space. And now we consider the collection of all those omega, from capital omega, from our probability space, such that G composed with X maps them onto some specific subset of the real space called B, right? And we take the collection of all those omega such that they are mapped thither. Well, that's also the same set as the preimage of B under this transformation, clearly. So the equality holds trivially, and we can use the independence of the variables, random variables xi, to write that this is actually equal to the product over J of P, and I will use the shorthand notation now, xi subset, or an element of the preimage gi of bi, and then we transform it back. So this is now, so basically we reverse this move. This is the product over J of P of gi xi as a subset of bi. We reverse the step above, right? And this is true for all Borel sets, which is precisely what we wanted to show, because this is the definition of mutual independence of some random variables. And this concludes the proof.